Hi there, folks. Welcome to another exciting edition of HL Chemistry Flipped Classroom. We're going to talk about molecular polarity today. Hope you're excited about that. Just like this young fellow right here, you might be looking at your computer with appreciation. Thought of doing another Flipped Classroom video. So as I said, we're going to talk about molecular polarity today. I found this interesting little template here or whatever for the PowerPoint's got a nice stage, and for some reason I'm picturing like one of these dancing frogs. You know what I mean? That kind of thing. So I don't know why, but that's what I'm imagining. And when I'm looking at this, but you know what? Enough with this silliness. Let's just get right down to it. Okay, so molecule polarity. We've talked about bond polarity and bond character. We were talking about individual bonds there, but now we're going to talk about molecular polarity. So the thing that makes this a little bit more complicated than what we talked about before is that molecules can contain more than one bond. So HCl, that's a simple diatomic molecule, but it only has one bond. However, water has two bonds, this bond and this bond. CCl4 showing you the true dot structures to keep you on your toes, because we will see those sometimes. This has four bonds, 1, 2, 3, 4. So what this video will be about is how polarities of different individual bonds interact to produce a molecule that may or may not be polar overall. So what we are talking about here is how these polarities of individual bonds interact to produce a molecule that may have an overall charge or a charge separation. There's kind of a weird term associated with that. It's called the dipole moment. But basically it means the molecule has some degree of charge separation. And this is the whole idea that we're going to be developing throughout this video. Now, molecules that do have charge separations are called dipoles for the simple reason that they have two poles. They have a positive and a negative side. Very similar to what you see in a magnet with a north and south pole. So when we have this charge separation, molecules get poles like a magnet, a positive side and a negative side. And again, in this video, that's what we're going to be talking about, the factors that lead to that. So this can be tricky, and we're going to look at it in several different ways. But if a molecule is going to be polar, the following requirements must be met. So at least one of the bonds within the molecule must have some polarity to it. Now, this is a classic example of the way chemistry builds upon itself. If you were a little shady or had a little bit of a hard time understanding that bond polarity thing, well, you're probably going to have a tricky time understanding this as well. So maybe go back and look at that video again or ask questions about it in class. But at least one of the bonds within the molecule must be polar, and the molecule must not be symmetrical. Remember, the whole thing that we're talking about here is we're talking about molecules that are dipoles, molecules where there's some kind of charge separation, some sort of difference between the sides. So when a molecule is polar, it leads to it is caused by a lack of symmetry in terms of how charge is distributed. Now, again, like we talked about with bond character, there's a continuum here. Some molecules are more polar than others, or you might say have a greater dipole moment than others. And some molecules are going to have no dipole moment at all. Let me see if I can pop myself out here for a second so you can see that very last bit. Some molecules are not polar at all. They have no dipole moment, and we call those nonpolar. So this ends up having huge consequences in terms of the chemistry and the way things behave. So there is very good reasons to understand polarity. It's going to affect a lot of other things, so you're going to have to be patient with me. We have to try to understand it first, and then I'll tell you and try to help you understand why it is that we're talking about this. But let's just try to get the polarity down first. So let's look at a couple of examples. So take the case of water. Now, this is why shape, hopefully I'm imagining we've been drawing Lewis structures in class, and we've been drawing shapes and talking about shapes. This is why shape is really important, and why we want to, if we can, draw Lewis structures with the correct shape. Water is a bent molecule. So water is a polar molecule. It's sort of a classic example, in fact, of a polar molecule. if we examine the requirements that we looked at earlier, it does have polar bonds. Oxygen's electronegativity is, I think, about 3.5. Hydrogen's is right around 2. So there's a difference in polarity between those. And it is also not symmetrical. Now you might say, hey, it's kind of symmetrical like this. And it is, but it's not really symmetrical this way. You got this oxygen on this side, and you got the hydrogens on the other. So therefore, it meets both those requirements, and water is a polar molecule. Let's look at another example, CO2. Now again, shows the importance of drawing our Lewis structures properly. This is the properly drawn, there's lines in front of it, but this is the properly drawn Lewis structure for CO2. CO2 is nonpolar. It meets one of the requirements, but not the other. It has polar bonds. The carbon-oxygen bond is a polar bond. Again, oxygen is about 3.5. Carbon is about right around 2.1 or something like that, whatever. But there's a fairly significant electronegativity difference. So these bonds are polar, but those polarities cancel. They don't cause separation of charge. They don't cause a negative side and a positive side. And due to symmetry, these cancel. And I'm going to show you kind of another diagram maybe to help you see what I understand, help you understand this a little bit. But symmetrical molecules are going to be non-polar. Now, if you're just talking simple binary molecules, so molecules that contain only one bond, really all you're strictly looking at is there electronegativity difference between the two atoms? You know, if we look up their electronegativities and just subtract them, right around a difference of 0.3 is where we'd start to call something pretty polar. Less than that, it's pretty much non-polar or very low polarity. So something like HCl, I think, you know, chlorine's polarity is like 3, hydrogen's is right around 2. So difference is 0.9. So this molecule is definitely polar. It is going to have a charge separation. It's not symmetrical in this plane that I'm drawing right now. Because you got to think about the fact there's a hydrogen on this side and a chlorine on the other. So when you're thinking symmetry, think just the arrangement of atoms and what atoms are involved. So yes, that one's polar. Now, your diatomic elements, Mr. Brinkelhoff elements, are always going to be nonpolar because, first of all, they're all symmetrical, and second of all, there's no electronegativity. By the very definition of being diatomic, there's always going to be no electronegativity difference between these atoms. So they're going to share electrons equally, and there's going to be no dipole moment. So just something to keep in mind when it comes to binary molecules. Now let's look at a little diagram maybe, or an animation, or I don't know what you'd call it, to help us see if we can understand this further. So we looked at this before. If you're dealing with two atoms, it's pretty simple. If one atom is less electronegative than the other, the more electronegative one is going to get a negative charge to it, partial negative charge. The less electronegative one is partially positive, and they have magnetic-like behavior. If we put them in a magnetic field, if the molecules are able to, they will orient themselves within the magnetic field. Now, if you throw 3 atoms in here, especially if we, these are called vectors. I'm going to talk more about these vectors in a second. So these 2 atoms are of lower electronegativity, and the B is of a higher electronegativity. So both of these bonds are polar, but overall, the polarities don't cancel because it's not symmetrical. If we turn on the electric field, we see that the kind of B end of things is the positive side, or rather the negative side, I mean, because this molecule is always orienting itself so that the negative side is attracted to the positive plate and the positive side is attracted to the negative plate. And so the overall polarity comes from kind of these 2 polarities added together, if you will, in both of these bonds. So the reason shape is really important is if you have, like, let's take the case of CO2. So in the case of CO2, both A and C would be oxygen. So oxygen's pretty electronegative. So let's do it like that to represent oxygen. And then carbon's a little less electronegative, so it's about like this. So yeah, both of these bonds are polar, but overall these 2 things exactly cancel each other out. So notice that now this molecule doesn't interact with the electric field at all. It's nonpolar. So shape is extremely critical, and it's extremely important that CO2 is linear. If it was not linear, well, then it would have a polarity, you see. Just to show this simulation does have some real molecules, water. Just another way to visualize it. We could look at electron density. So that the darker areas are where there's more dense electrons. So in the case of water, the electron density is greater around the oxygen end. So we do have a polarity here. This is because oxygen is very electronegative, and what it's tending to do is pull electrons towards itself in the molecule. So we do develop a dipole. We do develop a partially negative end at this end and a partially positive end. If you look at something like CO2, on the other hand, though, now we do not have a partially negative end and a partially positive end. Electrons are sort of being pulled towards this side and this side, but it doesn't lead to like a negative positive or a dark and light side. We could look at it this way too. It doesn't actually get poles. It doesn't actually get a true separation of charge like we get with water. Water, we have high electron density up here, negative, and low on the other side. Something like CCl4. Now that's a tetrahedral molecule. Tetrahedral molecules tend to, or really they'll always be nonpolar if all four of these are the same. So again, this molecule here, CF4, it's tetrahedral, it's nonpolar. There's no real difference in electron density on any particular side, so it does not have a dipole moment. So I hope that helps a little bit. Let's go back to the slide. Okay, again, I totally get that this can be really difficult for some people to wrap their brains around, but I want to take this moment to highlight the importance to you guys of really focusing in when you're watching these videos. You want to try to limit all the extra distractions that you can. In this world that we live in today, there's many things that can compete for our attention, and it's important when we're watching these videos and we're studying and whatever we're doing, whether it's in IB chemistry or elsewhere, to really focus in and try to focus on the task at hand. And we're almost done here, but I just ask, power through these last few minutes, even if you're kind of a little bit shaky on the understanding, and then next time in class you can ask me questions and we'll try to get this figured out. Okay? All right, let's keep going. A little bit more. I want to talk about vectors now, just a little bit about vectors. Now, some of you who've had physics before, this might be where you have a little bit of an advantage, but just the very quick 1-minute version of vectors, if this is a box here and this is newtons, which is the unit of force, if these two dudes are pressing on this box with this much force, of course the box is going to go in this direction, and it's as if they're pressing on it with 70 newtons of force. Those force vectors add. Now, if one dude's on one side and one dude's on another, the box will proceed in this direction still, obviously slower than before because the 40 newtons is somewhat being canceled out by the 30 newtons. Now, what if they push on each corner? So if you can imagine that, this box would kind of proceed in kind of a diagonal type fashion because it's getting a force this way and a force this way, and those vectors kind of add to a diagonal type thing. A little bit more, probably a little bit of a flatter than, because this guy's pushing a little bit hard. Anyway, it doesn't matter. That's kind of what vectors are, the very, very quick version. I hesitate to have you focus on it too much because we're not talking about like a thing moving in here. We're more talking about where charge is going. But we do have to have a little bit of a feel for vector arrows and how they work when we draw them on molecules. So you might be asked to look at the Lewis structure and put vector arrows on it, or interpret them at least. So I just want to spend a couple minutes talking about how that might be done. What you have to start with is a complete Lewis structure, hopefully with the correct shape and all that kind of thing, because the shape is pretty important. But what you want to do is, I've shown you those little arrows before. Well, we'll look at them again here in a second. But you always remember you want the arrow pointing towards the more electronegative element. And then, just like with those boxes, you kind of want to consider what would the overall polarity be if you summed up all those vectors. And then you could draw the resultant arrow, or you could draw the little partial positive and negative signs and so forth. So I'll show you what I mean here. Okay, so in the case of water, let me try to get my pen here. Okay, so we've already talked about water. It is polar, and the hydrogen-oxygen bond is polar, so this bond would have a little polarity vector like that, and then this bond would have a little polarity vector like that. And again, we make it with like almost like a plus looking sign. So the sum total of those two vectors, I wonder if I have a different pointer. Yeah, sure. The overall polarity would be something like this. Another way to do it is to draw these little funny S-looking things. This is the partially negative side of the molecule. This is the partially positive side of the molecule. Either way you want to do that is fine. Another example here, back to CO2. Again, this bond is polar. We got a carbon-oxygen bond. But these two are going to cancel. It would be somewhat analogous to on our little dudes back there pushing the boxes. If they were both pushing with 40 newtons on opposite sides of the box goes nowhere. Again, this isn't a movement thing, so it's only like roughly analogous to that. But still, these polarity vectors do cancel. We don't get a dipole moment here. No separation of charge. This is going to be nonpolar. You know, you might want to label it. Whoops, I don't know why I did that. Just to make it really unambiguous if you had to do this. So when you do this, when you're thinking about electronegativity, you know, I just do it by thinking about the electronegativity trends. You know, I know that fluorine is the most electronegative, and that's all I really do. You could look at that actual table in your data booklet that has the electronegativity values on it to see, because that's where it starts, right? Is there's a difference between electronegativities. Oxygen's is like 3.5, carbon's is 2.4 or whatever it is. The arrows are going to point towards the more electronegative one. So the way you figure that out is either by just knowing your trends or actually looking up the electronegativity values if that is available to you. Okay, so here's a couple more. We've got SO2, SO3, bent shape here. It's the kind of the 120 degree style of bent. There's two different bents. This is trigonal planar. So these are all on the same plane, and this is your classic tetrahedral shape. So what I want to do is just take a shot at drawing polarity vectors for the individual bonds, and then also kind of thinking about and drawing the overall polarity for these molecules. Again, it can be very tricky, especially at this point early on if you haven't had chemistry before, but give it a shot and see what you can do. Okay, let's go ahead and take a look. So oxygen is more electronegative than sulfur, and so there would be one kind of polarity arrow thusly, one kind of polarity arrow thusly, and the overall polarity would be, there's not really a significance to the size I'm drawing this arrow. I'm not really drawing it very straight either, but bottom line is this is the positive side. There's sort of a positive side of the molecule here, and a sort of negative side of the molecule kind of down here, or these oxygens. Whoops, I meant to say negative. That's negative, yeah. So this is a polar molecule with the sulfur end being the kind of more positive end. Now I suspect this molecule would not be very polar because you've got this lone pair right here, and that does matter. So that's a little bit of a tricky one, but I think there's going to be some polarity there probably. Now on this one, what's going to be the case is, notice we have three bonds that are the same. I mean, yeah, I know this is a double bond, but remember Vesper theory treats double bonds and single bonds as the same. They're totally exactly equal, and this in particular is kind of hard for people to imagine sometimes, but it's sort of like, if you can imagine a triangle, I don't know if this is going to help at all. But a triangle, and electrons are being pulled to like three corners of a triangle. That's not really going to create a dipole. That's not going to create a distinct positive and negative side. So trigonal planar ones like this, where all three of these things are the same atom, are going to be nonpolar. So this has no overall polarity, and this is nonpolar here. Very important that it's trigonal planar rather than pyramidal, and that all these oxygens are in the same plane. That does make a huge difference. This is tetrahedral. Again, I'll say this again and again, critical to imagine the shape properly. These are not all on the same plane. This is drawn in a way to kind of help you see that, but chlorine is more electronegative than carbon, so we would have three little kind of polarity vectors down here. Carbon and hydrogen have very similar electronegativities, So the carbon-hydrogen bond is pretty much nonpolar, but there is a slight polarity to it, which I should probably draw as like a shorter arrow, but oh well. So you've got these three things kind of going down. Overall electron density is going to be pulled down in this direction. This molecule is polar, with the negative side kind of down here and the positive side more like up here. Okay, folks. So thanks for watching. Like I said, this can be very tricky. We'll practice in class, and you can ask questions about it, and we'll get it figured out eventually. Because like I said, this does apply to a lot of other things and ends up being a super important concept in chemistry. So thanks for watching, and have a good evening.